little bit. All right. Good morning, Ethan. That's who this is for. We're going to find out, aren't we? Now he's going to listen to it. For sure he will be. All right. So today's class, even though it's called the Doppler Effect, will actually describe two things. I choose, if you're interested in reading and you're really interested in the subject, it's pretty darn cool. Chapter 4, I'm skipping. I'm going to give it to you in about 2 minutes, the entire chapter. It's not because it can be explained that easily. It's a challenging and very mathematical and sciencey chapter, and we don't necessarily need that much in a have I had the discussion about survey courses in college? You have these courses that are called survey courses, and it's usually like the first one. So I think next year they're offering geology here as an elective for science, or your science class if you want to make that your science class. And it's going to be a survey course as well too. So it's like the first time you take geology. Well, you don't get into like true great detail in a survey course. It's a really broad stroke look at the subject matter to see if you're interested in that. I was always interested in astronomy and geology, and I took both of those in survey courses in college, and it was good. Now the college course in astronomy was a bit more sciencey than what I'm making it, but anyway. So if you hear the word survey course, it just means you're a very general course on the subject matter. All right, so today, so chapter 4, I'm skipping. It's just too much detail. We don't need it for this particular course. I can explain it really quickly, and it's also really cool, and maybe you've heard about it in science class before. Hopefully you also have heard about the Doppler effect too. All right, so we're talking about two big things. I probably should change the title, but I didn't. All right, here we go. These are the two things, something called Doppler effect, something called spectroscopy. I think 2 years ago, Miss Newburn was trying to do a fundraiser to buy a spectroscope and stuff, and they're really expensive, but boy, are they cool. All right, where did we leave off? We were talking about emitters, and remember, emitter is something that literally produces that radiation. If we're talking about visible light, light bulbs make light. Apple pies do not make light. They reflect visible light. But there are other things or other parts of the spectrum where apple pie is an emitter. An apple pie emits infrared radiation. So it's not that all things don't emit things, or some things do emit, some things don't. All things emit some form of electromagnetic radiation. Typically, we're talking about thermal radiation. That was yesterday's class. The light, or I should say the light, the electromagnetic radiation that's produced when you heat something up. Okay. The classic example here is you heat a horseshoe, it starts to glow. It is literally giving off light. If it's heated up just a little bit, it doesn't glow. It's still producing, as that one video we saw, still producing infrared radiation. And if you use an infrared camera, then you can see that it's glowing. That's thermal radiation, right? Thermal radiation. The horse and the house, I mean, even the trees in the sky in the background are giving off infrared radiation as well, too. The explanation, it was a pretty good one of why does thermal radiation produce light? Remember, all atoms have electrons that surround the nucleus. They're all in what's called the happy state, except scientists decided to call it the ground state. The happy state is, I don't need to change. I'm happy where I'm at. If you interject energy into the ground state, it gets energized, it gets excited, and it moves literally to a different orbit. And then physically, it's a higher orbit. Kind of makes sense. More energy, just like spacecraft, you can have a higher orbit. When it decides that it's had enough of its excited state, what makes that decision is there's no more energy. I mean, it doesn't want to live here. It wants to live in its ground state. So if you're not constantly putting in more thermal energy into it, then it's going to want to go back to its ground state. Well, law of conservation of energy says that you got to, in order to go to a ground state, you got to give off the energy you just received. It gives it off in the form of a photon, a particle of light. And that's why when you heat things up, they glow, right? The more energy, the higher the orbit, the different frequency when it finally ejects that proton, and I say proton, I meant photon. When it ejects that photon, since it's in a higher orbit, it ejects it at a different frequency. And that's why sometimes it glows orange, sometimes it glows red, sometimes you heat it up high enough, you'll get all the colors. Max Planck was the guy that figured this all out. a younger Max Planck right here, German guy, we get this thing called a Planck curve or a black body curve. And remember, a black body is this imaginary, it's idealized, object that absorbs all radiation and then emits all radiation through a little tiny hole. If you plot the radiation coming out of a black body, you get this, hopefully by now, recognizable curve. This is an idealized curve of a perfect black body. Life isn't perfect, so the real curve looks more like the dotted line. So if you take a picture of our sun, you don't get this nice little blue curve, you get more of a black curve. And I did show you some real honest-to-God black body curves. The thing about black body curves, two things. One, as you heat an object, 300K is, I think it's about, my fan doesn't like your 72 degrees. If you're hot, you can turn it back down, but it'll survive. 300K, and I didn't really make this too, no, 300K is about 80 degrees Fahrenheit. So like a little bit warmer than what we're at right now. 7,000K, you're talking about the sun, right? Not the corona, the atmosphere of the sun, but you're talking about sun type heat, very hot, right? Melts everything. As you heat or you increase the thermal energy, the curve itself, the basic shape still looks like that blue thing right there. But what it does is it increases in intensity and it ramps itself up. It still maintains the same basic shape. And also, in this case, if we're talking about the frequency, not wavelength, it shifts to the right. If we're talking about wavelength, it shifts to the left. And as Matt pointed out, that some things, okay, room temperature, we can't see. Your body physically isn't glowing right now. You're not hot enough. In order for you to start, literally to start to glow, you got to be a very hot temperature. Okay? It would be pretty hard to make the human body glow. I mean, we would combust before we would glow. Metal is easy. You heat it up and it starts to glow. I never should have shown that picture. I was like, oh, I just recorded and put it on YouTube too as well. I was like, oh, I need to change that for next year. It's not as funny as I thought it was. All right. 71 gives you this graphic right here, page 71, empty space. 300K is this is 60K. 60K, 0K, remember 0 degrees Kelvin is what's called absolute zero. That's where your atoms stop vibrating and they're solid, right? Absolute zero. There is no thermal energy in the object whatsoever. Put a little bit of energy and it starts to heat up. 300K is about room temperature-ish. 600K, you know, this is a nebula. Here's a star right here. You can see that the peak moves into the visible, which is why suns produce lots of light. Here's a blue star. And remember, I made the paradox, and maybe it's not a true paradox. We think of blue things as being cool. We think of red things as being hot, right? Literally, wow, that's red hot. Blue is ice cold blue. It's actually the opposite of that. We're talking about thermal energy, where red is actually cooler than blue. Kind of crazy. This star right here, the bottom one there, is giving off more ultraviolet radiation. The peak is beyond the visible than it is visible. All right. So on to the new stuff. I said we're going to do two basic things. So keep this in mind. We're still going to come back to this here in a second. The but here is this. And there's going to be a couple videos. There's a huge problem with this basic idea of Planck curves. It works great. 100% true as long as things are in motion. If things go in motion, we get this big, huge problem that today's class is about. Anybody notice it? It changed pitches. The sound you heard of a moving object, the horn doesn't, like there's some guy there's blowing a horn like, oh, give you a higher pitch, lower pitch. The horn is just one. If you were standing on the train, you would hear one pitch, perfect pitch, never stops. Yet the observer who was standing there not moving heard multiple different pitches from a pitch that isn't changing. That's nuts. Now, well, how about a different one? I mean, completely noticeable. You don't have to be a scientist to say something weird is going on. If you've ever, and all of you are mostly driving right now, when you're driving, you honk the horn, right? The horn doesn't change its pitch. Yet clearly in that video, I mean, anyone can tell that the pitch is changing. The question is why. You have or have not been taught about the Doppler effect? No one? Other than, okay. So this is the dude, forehead dude, right? Christian Doppler. He is the guy that figured this out. The question is, why did it take so long? Well, the issue is, well, up until the age of steam, we couldn't make objects that went fast. You only notice this effect about things that are moving with rapid velocity. If I talk and I move to you, like the train, my voice, technically it's changing, but so slightly you can't perceive it. As I walk towards you and walk away from you, the pitch of my voice is changing. You just can't perceive that change. Get something fast above, like, say, 20, 30 miles an hour, and all of a sudden, wow, that thing really changed. Why did it take so long for somebody to come up with this? It's in the 1800s, because we didn't have things moving that fast, right? Christian Doppler actually didn't look at trains, right? He looked at what are called binary star systems. A binary star system is a solar system that has two stars. He was Austrian, right? And he studied these things. And what he noticed was something rather peculiar. He could tell that he was looking through his telescope two different stars. And what he noticed was sometimes one of them was this color, and the next time around on the opposite side, it changed colors. And he was like, how in the heck is this happening? He's the guy that figured this out. He also connected this idea with what we just saw in those two videos. It's connected with sound. And that is because both sound and light both propagate through a wave. And so anything that makes a wave exhibits this thing that's named after him called the Doppler effect. And it's pretty easy to understand. It's that thing that you heard with the sound. That as the thing approaches you, the sound sounds the same, but as it goes past you, all of a sudden the pitch decreases. Paradoxically, that's not really what's happening. Christian Doppler found out what was really going on. And here's what he found out. If you have a stationary car that's honking its horn, the waves of that sound go around 360 degrees forever until it's attenuated by, I don't know, things in the atmosphere, things on the ground, right? You go 2 miles away, you might not hear it. It's not loud enough. If the car is not moving, no matter where you stand, it sounds like, I don't know, I'm not a music person, and the note of a D sharp or something. I made that completely up, right? But the pitch doesn't change. If you look at the wave, it would look like this. As soon as either you or, like I said, I completely made that up. As soon as you or the object starts to move, and by moving, I mean at a relatively rapid pace, you won't notice this if the car is moving 5 miles an hour. Make it go 50 miles an hour, as we saw in that video, and you hear this thing. So what is going on? All right, not to get too math on you, but remember Hertz was the guy that figured out for wavelengths. He's this guy that said, how many times a second does this wave repeat itself? So it turns out sound goes anywhere between about 20, that's 20 of those per second, all the way up to about, for our ears, about 20,000. If you're an adult like I am and you're in your 50s, almost 60s, right? You can't hear high frequency pitches. Like your ears go bad when you get older. And so that's just why your parents don't, you're like, ow, turn that down, it hurts. Old people can't hear higher frequencies. They don't mind. Going off on a tangent.
My mom is the one that says, tell me to turn music.
She is, because she can hear the low stuff very well. All right, so 856 hertz is just a frequency. We call frequency in terms of sound, as we call it pitch or tone. Okay. As the car moves, its frequency changes. As we hear that, we perceive that change in pitch as a change in tone, right? The frequency is changing. So what's going on? If the car isn't moving, it's producing 856 hertz. We hear 856 hertz. All right, let's make the car move. As the car moves towards you, right? As it moves towards you, why did I change it from 856 to 256? I don't know. Why didn't I make it 856? All right. It doesn't matter. Whatever the number is the number. Remember, hertz is how many times per second that the wave repeats itself. As the car, if I go back to 856 now, I'll be upset. As the car starts to move, more moves towards your ear. Now I'm back to 856. All right. What happens is the car is catching up with the sound waves. Even though it's producing it, as soon as it goes past it, the car is moving as well too. So it's closer to those wavelengths. You get compression on this side. You get stretching on the back side. Compressing on the front side, stretching. Remember, these are frequencies, right? If you measure how many of these pass in 1 second, that's the hertz. Well, check it out. Now there's more of them. This is why as the train or car approaches you, you actually hear a higher pitch. And as it passes you, you get a stretched out, you get a long. There's fewer of these per second. This is why the tone drops. This only happens if the object is coming towards you or going away from you. If it's staying the same distance away or you're moving with the object, you will hear the same frequency. But as this goes towards you, hey, you got more waves per second. Therefore, you get what's called a frequency change. And the frequency will appear to you to be higher. I'm making these numbers up, but you get the basic idea. As it goes in the opposite direction, you hear lower. So as the car goes away from you, it's stretching out these. That means there's fewer of them per second. Therefore, instead of hearing 856, I made these numbers up, you hear maybe 556. That's this effect that's called the Doppler effect. Now, this is for sound, but it applies to all things that make waves, including water, right? If you can imagine yourself, if we had a wave-producing device, somebody's putting their finger in and out of the water, right? It makes waves. And you had, here's the finger, right? It's making these waves, right? If you were in a boat, right, traveling towards the waves, and you have a fast enough speed, you're going to hit more of the waves per second than if you were driving away from it. It's the same effect. All right. We could. But once again, as it's traveling towards you, you don't perceive an increase of pitch because it's already has compressed waves. The time that you hear is when it passes you, and it switches from that higher to low. Notice as it continues to go, it doesn't continue to get lower and lower and lower and lower. The only time you notice that actual change is immediately when it passes you, and it switches from that higher frequency to lower. But here's the kicker, or the paradox. Neither one of those tones you just heard is the actual tone. It's somewhere in the middle. It's somewhere between that high pitches you heard as it came towards you and the low pitches at what? Somewhere between the is the actual tone. Right? One more time with the button. You can't hear it decreasing. It passes you. As it continues to go past, it doesn't get lower, it stays the same, but there's a definite shift between that higher pitch and the lower pitch. All right. The bud here is also, remember, it doesn't have to be the thing that's producing the sound to be moving. You could be moving. As the skateboarder approaches the radio right there, he's going to hear a higher pitch. He's got to be going pretty fast, right? Now, 1 second. And as he goes past, he would hear a lower pitch, right? He'd have to be going relatively fast, over 20, 30 miles an hour. Yeah.
So does the Doppler effect happen with like people on roller coasters do?
Well, for sound, it would,
yeah,
certainly.
like if they were screaming and passing you.
Yeah, 100%, 100%. So if you stood in, I've done this, some roller coaster, it's like a picture zone, you stand there and it goes past you. You have to be paying it, usually you're not paying attention to it, but next time you're there, absolutely, because roller coasters go pretty fast, you will notice it. All right, he's the guy that figured it out. Now remember, he didn't do it with sound, he did it with binary stars. As he noticed, so you can imagine a binary star system, two stars rotating around each other. Sometimes the star is coming toward you, sometimes the star is going away from you, but he saw the same thing. The difference is that for light, frequency change is expressed as colors. Okay, we better write some stuff down. So first thing we're going to write down is what's called the Doppler effect, named after Christian Doppler. It's a change in frequency of a wave. It doesn't say anything about whether it's a water wave or a light wave or a sound wave. It just says a wave. Anything that propagates as a wave will exhibit the Doppler effect. Caused, yeah, well, then you don't notice it. Caused by the motion of the observer or the object or both. If both objects are in motion, right, it compounds that effect. You get a larger Doppler effect. The speed of the object or objects depends upon how much of a change you will see. Speed of sound is about, at sea level, it's somewhere in the neighborhood of 700 miles per hour. I'm doing some rounding there. If you are in a car traveling pretty fast, 100 miles an hour, right? Towards a lightning bolt,
Oh, God.
right? The crack of the lightning you will hear would be higher pitched than if somebody was standing next to your car when you heard the sound. Two people, one moving 100 miles an hour, one stationary. You're going 100 miles an hour and you pass a person standing still and you both hear the same thing. The person standing will hear a different thunder crack than the person in the car, simply because of the Doppler effect.
Screaming really, really loud.
Well, the screaming comes after the thunderclap, not during. Last spring, myself, Miss Allen, Mr. Surratt, and Mr. Cownell were playing golf, and we got caught in a thunderstorm. Or was that this fall? No, that was this fall. Yeah, that was like August, September-ish. And we almost got hit by lightning. It was pretty fun. Miss Allen was screaming. And then it started to hail on us and we ran really fast. All right, Doppler effect. Applies to all waves. I don't care whether it's sound, whether it's water or light, Doppler effect takes into account. Now, astronomers, right, you can't yell to the moon, right? Sound doesn't travel through space, but light does. So astronomers apply the Doppler effect specifically to light. All right, quick tangent. All right, we've talked about this many times. My assumption was this made sense to you. If I threw these words out and it never made sense to you, here's what it means. Roy G. Biv, from left to right, from lowest frequency to highest frequency. These are the frequencies in nano, millionths of a meter. These are the numbers of the frequencies, how many billionths of times per second that it repeats itself. So for instance, red is somewhere around, we'll just call it 700. So 700 nanometers. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay, cool. The issue with the Doppler effect is this. Our sun is yellow. If you're screaming, you got to be going pretty fast, and you're going towards our sun, you don't see yellow. Just like the train, you hear a higher frequency. So if you're going really fast and you're going towards our sun, guess what color our sun is? I don't know, it could be green. If you're going in the opposite direction really fast, we're not talking about 1,000 miles per hour, but we're talking about fast. Our yellow sun will actually appear red to someone going away from our sun. We give these two ideas a name. If you're going towards an object, you're actually going towards the color. And I don't know why they didn't choose violet. They actually chose blue. If you're going away from an object, you're actually going towards the color red. I don't know why they don't call it a violet shift and a red shift. But for some reason, indigo and violet, nobody liked them. And they call it a blue shift or a red shift. And it indicates which direction you're going towards. Right? Remember, the Doppler shift applies to sound. We just saw that in the video. So as the pitch increases, you're going towards the object. You're moving towards the object. What?
Write this down.
You need to understand the concept. I will ask you about a blue shift or a red shift and ask you, is it going towards you or going away from you? Right? So you can write down as much or as little as you need here. I will not ask you any questions about sound, but I will ask you about light. If you're moving towards the object or the object is moving towards you or both, right? The pitch increases, except we don't have pitch for light. We have colors. You're moving towards the blue. So we call that a blue shift, right? Why didn't it call it indigo or violet? I don't know.
So if you're moving towards something,
If I could run really fast towards you, or Danny, or wait, who's got red on? Nobody. Everyone's got blue on. This doesn't work. Wes has got a red shirt. Literally, like no joke. you can't run this fast. But if you could run a couple, close to a couple 100,000 miles per hour, his shirt would actually appear to you to be blue or green or indigo or violet. It wouldn't appear red. Conversely, if we could run away from Danny, right? We're talking hundreds of thousands. You can't run the speed of light, but as you approach the speed of light, and as we look back, and I'm looking at Danny's shirt or jacket on that he's not supposed to have on, right? His jacket would appear to be potentially red, depending upon how fast I'm going. That's craziness. It's not craziness if you think about the sound. I mean, we literally just saw 2 videos, and you've probably seen that in light. It's not an imaginary effect in the sense of it really happens. Okay, so the opposite of this is when you're running away from each other, right? Either you're moving away, the objects are moving away, or both. Okay, we call this a red shift because the pitch decreases and the light shifts towards the red. Once again, in the sense of, is this really occurring? The answer is no. Danny's shirt is blue, jacket is blue. It's always blue. It's always going to be blue unless he bleaches it or something, right? Or leaves it out in the sun and gets faded. But if we increase velocity of the observer or of Danny, the apparent color will change. His jacket still is blue, it just doesn't appear blue, right? Why is this a big problem in astronomy? It's because we observe astronomical objects with our eyeballs or with optical instruments. So when we look at a blue star, the question of that is, yesterday we had this whole thing like, hey, we can look at the Planck curve. It's blue, therefore I can tell you how hot it is. No, you can't, because you don't know how fast the object is moving. So even though the star appears blue, the star could actually be yellow in reality. So Doppler, although he discovered this, created a whole big problem for astronomers. Now we can't just look at a star and say, look, a yellow star. You don't know if it's a yellow star. We know our star is yellow, but we don't know whether we observe another star in the heavens, whether it really is yellow, or maybe it's a red star, or maybe it's a blue star, a green star, right? Anywhere in between, because the Doppler effect, everything is moving. We've already talked about that plenty of times in astronomy class, where the galaxies are moving, the solar system, everything's moving. So these blue shifts and red shifts are occurring. The question is, how can we tell if they're moving and how fast they're moving? That's the second half of this lecture. So yesterday we got this great new thing. Hey, I can tell the temperature of a distant star. No, you can't, because of the Doppler effect. So this problem had to be solved. And once again, the big problem with astronomy is we can't go to that thing and say, oh, stopwatch, let's measure it. We can only observe the radiation coming from it. Luckily for astronomy, some more smart people came in and told us how to tell the velocity of objects without actually looking at them. Now we can tell the velocity of some objects, well, using Kepler's law, we can figure that out for close things in, but some things are moving, but we can't see a full rotation if it's even making a rotation. It's like a galaxy, not moving in it's not spinning around us, it's moving away or towards us. So we need a new technique. All right, we okay? Chapter 4, its entire chapter is about this technique. Okay? Technique of determining how fast an object is moving just by looking at it and not like doing a geometry calculation. All right. No. Some more slides from the book. Space shuttle moving towards objects. Any object that it's moving towards will shift towards them. That doesn't mean it's blue. Could be, but it's having a blue shift. All the objects behind it are being red shifted. Doesn't mean they're necessarily red. It just means they've been shifted to a longer wavelength. Okay? Space shuttle only went about 16,000 miles per hour. And therefore it still would exhibit some redshift. Now, the interesting thing is the stars that are perpendicular to it appear normal in the sense of you're not getting closer or farther away. Are they really that color? Well, they're moving away too, potentially, so they are being Doppler shifted, but not because of your motion.
Is that like the hyperspace times in Star Wars?
Yeah, and that's what they're trying to show is red shifts and blue shifts a lot of times in science fiction. All right, a couple notes on the Doppler effect. It is widely used, it has to be. All the objects in the universe are in motion. If you don't take into account a Doppler shift, then you don't know anything about your data. Remember, the only data we get from distant galaxies are electromagnetic radiation. And since those galaxies are in motion and we're in motion, then they've been Doppler shifted. Shifted blue or shifted red. That's the problem. Got to figure that one out. All calculations on the spectrum that reaches our instruments, we have to take the Doppler effect into effect. Distance has no change by this. I mean, like you see the same Doppler effect whether the thing is 100 light years away or 1,000,000 light years away. It only depends upon how fast the objects are moving and in what direction. The same Doppler effect is an effect on Jupiter as it is on the Andromeda galaxy. Distance doesn't have any effect in the sense of increasing or decreasing the Doppler effect. Speed does. Speed is the thing that has that effect. Lastly, remember this. The Doppler effect is just a perceived change. Danny's jacket is blue.
It's actually green.
Oh, dear Lord. His shirt is green. His jacket is blue. But if he gets into motion or we get into it, it's got to be fast motion. For light, we will never observe as in human speeds. We will never observe the Doppler effect. We will observe it for sound, but not for light. Jacket isn't actually changing colors. The perception of the color is caused by the velocity change. All right, we okay? We will probably finish. I'm not going to stop right here, but we'll probably finish this lecture tomorrow. This is the end of the chapter. If I do finish it tomorrow and there's more than, let's say, 10 minutes, I'll start the next one. Long story short, that means quiz on Monday.
Do you think that you're going to have school tomorrow?
They said 1 inch of snow. We're going to have school tomorrow. I don't know. Maybe something weird could happen. Earthquake.
Ready, gone, is that right?
Oh, I don't know. It's still going pretty good. I think the snow.
Yeah, it's not supposed to stop snowing until 3, and it's sticky.
They should send us home early and then they'll school tomorrow. That would be awesome.
It would be awesome. Ain't gonna happen. All right. How do astronomers use the Doppler effect? Okay, so recall from last class, we had this thing called the Planck curve, right, or the black body curve. As we look at this blue star in our instruments, we make this nice, pretty idealized Planck curve right here. Remember, the real one doesn't look like this. It's got more jagged peaks to it, but it's got this basic shape. The issue is astronomers know that stars are moving. Is the star really blue or is it yellow and it's just been blue shifted? That's what they have to answer. So astronomers have to look at their curve and make the adjustment. But the issue with that is, well, how do they determine how fast it's moving? Well, they also got to take into the fact that we're in a galaxy moving away as well, too. Okay, I don't know what that star is right there, but you get the basic idea. Chapter 4 answers that question. I'll give it to you. It won't be 2 minutes, but it's short and brief. This is really cool. And if you don't understand why this is cool, then you're not a human being. This is some really cool stuff right here. All right. So chapter 4. So we got to go way back in time to 1801, a guy named William Wollaston, right? I'm sure I'm butchering his name. So what did he do? He's the guy that took light, held up a prism, and guess what happened?
Rainbow.
He made a rainbow. Was he the first person? Clearly not. By the way, what are rainbows? Light going through a prism, but where's the prism on a rainbow? Rain, right? The little rain droplets, right, act as a prism, and the prism effect is it breaks light up into its constituent parts, right? Why is it that we can see light? And that's because it has to do with frequencies, and it has to do with those different frequencies going through a medium that's not air. Turns out that we get this effect as long as if we can speed up or slow down the light in any form or fashion going through a different medium. We get this rainbow effect. All right, so Wollaston was like, hey, look, we get a pretty rainbow going through a prism of glass. Great. That's what he gets credit for. Along comes this guy named Joseph Fraunhofer. Fraunhofer discovered something amazing. he actually looked at the rainbow in detail. Was he the first person? We don't know, but he's the one that wrote it down. He gets the credit for it. It turns out, maybe you've done this in science class, maybe you haven't. If you just take a prism and you break up into a rainbow, it makes a pretty rainbow. But if you really look at the rainbow, he did, so did others, this is what really happens. If you really look at it, you notice I got a nice pretty rainbow, but I also get each, and this is a special prism that breaks it up into its literally the colors, Roy G. Biv. But what do you notice in this picture?
Green and yellow run together.
Coincidence.
There's
Instrument
like
thing.
4 lines of purple,
There's what?
like 4 lines of purple.
Blue, indigo, violet. There should only be 2, right?
Yeah,
What else do you notice? Look at the picture. What stands out?
Some of the colors are supposed to be lighter.
Okay. What else do you notice? You still haven't. Fraunhofer is frowning upon you. What do you mean by that?
like they're not popular, like
Oh, I see that. That's just coincidence. It's based upon the preciseness of how the instrument was made. What is another obvious thing that you can see?
They're lines.
What do you mean by that?
They're like little-
There's little black lines in the colors. And people for a long time, I'm probably making this part up, probably thought it was, well, I screwed up my prism. Maybe if I could make a better prism, I wouldn't get these ugly little tiny black lines. Fraunhofer said, oh no, there's something going on there. These little tiny black lines is what literally gave the answer to, well, how do we know how fast an object is going? What? I better explain that one. Every one of these lines, maybe not the bottom one, has little tiny, this is light from the sun, by the way, and we'll see this one repeated a couple times. Every one of those lines has little tiny black lines. Sometimes the lines are thin, sometimes they're thick, right? First time they were doing this, they chalked it up to inaccuracies in their instruments. Turns out there's not, and Fraunhofer was the one. He's the first person to write it down. He said, this is something, so guess what we call these lines? It's not a big stretch. Guess what we call those lines?
Fraunhofer.
We call them Fraunhofer lines, right? That's how science works. Write it down the first time and the thing gets named after you, or you get to name it, okay? All right, so these are called Fraunhofer lines. Great, happened in 1801. He goes, there's these, Fraunhofer, yes. Discovered lines in the spectrum of light, visible light. Fraunhofer. And those lines are called Fraunhofer lines.
When did you do it again?
18, well, actually, no, it says 1817 right there.
What is it?
Fraunhofer, he probably wasn't the first person to see this. Anybody with a prism could see this. He's just the first person that said, this must mean something.
I mean, what are we writing?
Fraunhofer in 1817 discovered spectral lines. Those are lines in the light spectrum. They're vertical. They're not horizontal. He takes a prism, makes a rainbow, and he goes, look, black lines. Must be something. Okay, great. Nobody knew what they meant. Studied for a while. Further scientists found this. At the time, there was this like, they were discovering new element after new element after new element. It was really a thing to do. Hey, we're discovering through chemistry. Chemistry was being brought to the forefront now. They were discovering new elements. Hydrogen is not a new element, but there was a lot of study of the elements. They could make hydrogen gas lots of ways. They take hydrogen gas and they burn it, okay, in a darkened room. Guess what they did in the darkened room with burning hydrogen gas, besides suffocate? They stuck it up to a prism. Here's what they saw. They stick burning hydrogen up to a prism, and they saw this. They didn't see this, right? All the colors. They saw one black line, and in the black line were little tiny slivers of color. They didn't see Roy G. Biv. They saw one black line, and in the black line were little tiny lines, and each line had a different color. Right? Interesting. Okay? Didn't know what was going on here. Like, why don't we see the rainbow? I mean, yellow light's awfully close to the sun. We say our sun is yellow. How come we don't see this? Instead of seeing this, we saw this. More black than color. Okay. Well, these lines are still called Fraunhofer lines. Okay. We call these spectral emissions. Those are the lines emitted from light. Right. All right. We better write some more stuff down. So what was being born was this thing called spectroscopy, a big fancy word. And it basically says that things can be identified by their fingerprints of spectral lines. Turns out that hydrogen has a specific spectral line. Burn carbon, you get a different spectral image. You still get a black line, you still get little tiny lines of color, but you get a different one. So scientists around the world ran around like, wow, this is really cool. And they would burn things. And they would put a prism up to it, and they would find the fingerprint of that element, which now allows you to identify unknown things. Hey, I don't know what this is. Light on fire. Heat it up until it starts to glow, and then put a prism up to it. Look at the lines, compare it to the known lines of elements. You knew what was in there. I mean, the issue is this, is that like this right here, plastic and felt, right? It's made up of lots of things. There's some carbon, there's some hydrogen, oxygen. I'm sure there's plenty of other things. If I light this on fire, heat it up so it glows, right? Put a prism into it. I'm not going to get just some lines. I'm going to get lots of lines because it's made up of many different elements. But you can easily, through a little bit of deduction, right?
Burn the world.
Well, that too. But you can easily say, well, I think maybe there's hydrogen, and match it up to the hydrogen fingerprint. Say, oh, look, there are the lines of hydrogen. Oh, there's the lines of carbon. Okay. These two dudes right here, this guy is literally Bunsen, named after, or he's the guy that the Bunsen burner is named after. Why? Because they wanted to light things on fire and hold prisms up to them. Well, the problem is you need to have a good burner to do that. And he's the guy that came up with, this is the way better burner. Like we still call it a Bunsen burner. He's the guy who came up. These two guys, Kirchhoff and Bunsen, yeah, that guy, Bunsen, right? They're the guys that put this whole thing together and kind of figured it out. Okay. So we start off by observing light through hydrogen, right? So they took hydrogen gas and they shone light through it, right? And they got this image. Wait a minute. Now I see the whole spectrum. What makes sense? Because I'm either doing light from a light bulb, not them. They were doing sunlight. Hey, I'm seeing now all the colors, but it's kind of reverse of the burning hydrogen. So if you compare that to burning hydrogen, what do you immediately notice? The lines match up perfectly. Why is this important? Because this is sunlight. So guess what you can say about sunlight? It must have hydrogen because those two lines are missing. It's not that it's absent of hydrogen. It's just that anything that has hydrogen, when you look at light going through that object, will have the same spectral lines as burning hydrogen. It's just that those lines are missing. It's not an absence of hydrogen. It's that it has hydrogen. These two things are what astronomers ran with. And what they ran with is the fact that now I can point my telescope at the sun, shine the light through a prism, and from the spectral lines tell exactly what the sun is made up of. This is how the sun was discovered to have a whole bunch of hydrogen, is because the sun has the spectral lines of hydrogen, like literally, and helium, and a little bit of iron, and a little bit of carbon, lots of other little things. Our sun has all that, and they were able to discover that, including today. How do they know that Jupiter is made out of this? No one's been to Jupiter. We can only study the light coming from Jupiter. They do it through spectroscopy. Big, huge thing. I still haven't answered the question of how does this answer the question of how fast an object's going. I'm going to stop right here, and we'll finish it tomorrow. By the way, spectroscopy, this is why Ms. Newberg wants one, not because she wants to do astronomy, but because she wants to say, what's this made of? Let's burn it. Puts it in the machine, heats it up, burns it, and then you get this analysis out of it. They're not called mad chemists for nothing. All right, Ethan, we'll finish this tomorrow, and then we'll have the quiz on Monday, and hopefully I see you back on Monday.
Why would you see us on Monday?